Hi, well, I'm here to help you out with another installment of electrochemical cells. What we're going to do this time is sort of lay out what the Nernst correction to what we think the cell potential will read out to be. So this is the same copper-silver cell that we looked at in the last video. And I've just highlighted the fact that this is the number we're interested in reading, the cell potential. It's called E cell. Same thing as before. We've got solid copper here, copper electrolyte here. The difference here is that instead of having 1 molar standard concentration of the copper electrolyte there, I've changed that to 0.1. Same thing here on the cathode. I've got, instead of 1 molar electrolyte solution, then it's a 0.1 molar. And so now we're going to see how that affects the cell potential. I've written down for you again what the net ionic reaction is. And just to go through that again, we have solid copper right there on that lead. It's getting oxidized to copper 2+, and therefore those copper are going into that solution. On this side here, where I've got silver 2+, picking up those electrons that are coming down the wire to form solid silver with an oxidation number of 0. And I put 2's in front of it, of course, because every silver needs to pick up 1 electron, and every copper will give up 2 electrons, so that balances that out. Now, it turns out that number that I just mentioned is pretty important. N is equal to 2 for this reaction as written. N is equal to 2. And previously we had already calculated that E0 for the reaction was 0.46 volts. So I'm going back to this equation now. This equation, it actually has a name. It's called the Nernst equation. Okay, and it tells you, now I've included the Nernst correction to give the full Nernst equation. So we already know this term, E0 for the reaction, that's 0.46. How do we figure out the correction? Now, and here's the formula for the correction. The Nernst correction says it is equal to this number, 0.0592, divided by N, and that's the N that we've already calculated for our stoichiometry, times log of Q. Now this Q is the mass action expression for the net ionic equation. So it's pretty straightforward. The only thing that's even a little bit tricky about this is that when you're calculating a mass action expression, we get to ignore, we don't even write in there solids or pure liquids. There's no pure liquids in this case, but there are some solids. So if you want to give a shot at that, why don't you write down the mass action expression for Q given that net ionic reaction. Okay, here's what I think it ought to be. I'm going to say Q is equal to, now the products, I see a copper 2+ over there and a silver solid, but we get to ignore the solid. So that's going to be the concentration of copper 2+ upstairs. And now downstairs under the reactants, and once again there's a solid, we get to ignore that, but I see silver 2+, it's got a stoichiometric coefficient of 2, so that means I need to write Ag plus squared. Okay? That's all fine. Now we actually have numbers for these because I know that the concentration of the copper 2+ is 0.1 molar, so that would be 0.1 molar upstairs, and downstairs the silver ion electrolyte concentration is 0.1, and that's squared. So I have a 0.1 over a 0.1 squared, which is equal to 10. Okay, and of course you know that log of 10 is 1. Okay, so that's going to go there. Log of 10 is 1. So the Nernst correction looks like it's 0.0592 divided by 2, which is 0.03. Okay, 0.03 volts. So what's in the end our answer? Well, our answer, the cell potential that we'll read off here on the voltmeter, will be 0.46 minus our correction, which is 0.03 volts, or 0.43 volts. That's the cell potential that we'll read right off there. when the concentrations of the electrolytes are not their standard value, which is 1 molar.